We'll now verify that Gauss's law works for our example of the infinite line of charge. Recall from the last pre-lecture, we determined the direction of the electric field produced by an infinite line of charge to be perpendicular to the line, and its magnitude to be proportional to lambda, the charge density, and inversely proportional to r, the perpendicular distance from the line. We'll now calculate the flux produced by this line of charge that passes through a cylinder of length L and radius r centered on the line. The flux through the two ends of the cylinder must be zero, since the field is parallel to those surfaces, giving E dot dA equals 0 everywhere, just as was the case in the circular plane that connected the two hemispheres a few slides back. Therefore, the total flux through the entire cylinder is just the flux through the barrel of the cylinder. This flux is easy to calculate, since the field is everywhere perpendicular to the surface, and the magnitude of the field is a constant over the surface. Consequently, the flux is just equal to the product of the electric field and the surface area of the barrel. The surface area of the barrel is just equal to the circumference of the circle times the length. When we substitute our expression for the electric field into our expression for the flux, we see that the flux through the Gaussian surface is just equal to the product of the charge density and the length of the barrel divided by epsilon naught. Now, since the product of the charge density and the length of the barrel is just the charge enclosed by the barrel, we recover Gauss's law, as promised. We chose to calculate the flux through a cylinder because the calculation was relatively simple. In fact, the result, that the total flux through a closed surface being equal to the enclosed charge over epsilon naught, is totally general and holds for any surface you might choose. You can consult the text for an explicit calculation for the case when the surface is chosen to be a rectangular box.